Okay, let's do a simple example of projectile motion. This is one that's similar in the textbook, but there's lots of different features about this example, lots of different opportunity for review about one-dimensional motion, graphs, setting up the problem, and so forth. So let's say we have, it's a very, not necessarily a memorable example, but not necessarily a memorable example, but we've got a projectile, yeah, that's launched like a meter above the ground, 1.0 meters. And it's launched horizontally with an initial speed v0. And let's say it hits the ground 3 meters away. 3 meters here. And so what is with this information alone, we can actually determine the launch velocity. And then once we've determined the launch velocity, I'd like to determine the impact, or the final speed and the impact angle. So this would be V1, be theta 1, and we got theta 0 over here. Theta 0, theta naught. Okay, that's the basic picture. Now, problem-solving strategy in physics. This book, really suggests that you do a step-by-step approach to these problems, and for good reason. I mean, you can't do any physics without a coordinate system. So that's the first thing we need to establish before we can make any notion about position. For a lot of these problems, the coordinate system will be obvious. Right? You've got an x-axis pointing upward and to the right, y-axis up. Our origin, it seems easiest to make the origin just right here at that corner. So that's our coordinate system. We got our coordinate system set up. Now the next step is symbols, right? We got to define symbols at each step. So we'll make, what do I mean by symbols? Well, all that we know is just position, velocity, and acceleration in time. And so those are the symbols that we're going to use. It'll be x0, y0, and then Vox and Voy, as I like to call it, v sub 0x and v sub 0y, and then t0. Right, and all that is for the projectile at the first step. I used to do this in class, like do a demo where I have like a projectile launcher and load the thing up and shoot it off and measure it, and that 3 meters would be the average value. So, and then this is the second spot. We've got x1, comma y1, then v1x, v1y, and then t1. All right, so we got position, velocity, and time stamp at every step. And then obviously in the middle, we got an acceleration, maybe a sub y, right? So this is projectile motion. So that is the picture, that's the symbols. What do we know? Right, that's the next step of this problem-solving strategy is, what do we know? And so we write that down in some spot. And, in this example, we know initial and final positions in both directions. So it's more convenient to use just delta x and delta y for displacement. These are vectors, so they need signs. So this is plus 3.0 meters. And delta y, this will be important later, but delta y is minus 1.0 meters. Right, you go down. I mean, we can draw that quickly on the figure. This is our delta y vector, and this would be our delta x vector. You don't want to draw too much on the drawings. I mean, it might even be better to draw another picture, because at the same time, you don't want to have it so scanty to where you don't understand what's going on. But anyway, that just takes practice. We know that V0y is 0. And since this is projectile motion, we know the value of g, meters per second squared. What else? Do we know anything else? Technically, I mean, T0 is 0, and we don't know what T1 is. for a lot of these problems, we generally deal with time intervals rather than actual time values. And then what are we trying to find? Well, we're trying to find, and this is where some abbreviations can come up, we're trying to find the x velocity. And we're going to use 3 equal signs to say that is equal to v0x, which from the problem, we know is equal to v0y. Those are all the same because we're in projectile motion, right? We're not increasing or decreasing speed left or right. If we did, then it wouldn't be as simple of a problem as acceleration downward. Okay, so that's a good setup for the picture and the pictorial representation that the book offers. So that's the setup. Graphical, I'll talk about the graphical part near the end of the problem. What's the next? So what's really the step? Or really the first step before we did this visualize stuff is technically how are we going to model the problem? And it's in the projectile motion section, so it's assumed that we're going to model it as projectile motion. So the model is that, slightly out of order, is that in the x direction, we have, and we can even use all our symbols that we have here. x1 equals x0 plus v sub x delta t. That's the only thing that we've got in the x direction. What about in the y direction? Well, we've got v1y equals v0y minus g delta t. That's the first one, right? When we integrate the acceleration. And then the next one is delta y equals v0y delta t minus 1/2 g delta t squared. And then the final one is v1 y squared equals v0 y squared minus 2g delta y. There we go. And so that's our model. I mean, uniform motion in the x, constant acceleration, more specifically free fall in the y. And so now we're really done with all the setup. Now the solve step that the book offers is, there's no like simple suggestion. Well, let's just kind of solve the problem. What do you need? You're going to need, well, what do you need to find? We need to find Vx. Okay, so let's look at our model and see where v sub x shows up. The only place it shows up is right here. And so obviously we need delta x and we need delta t, right? So to solve, right? So we know that Vx, thing we're trying to find, is delta x, which we know, over delta t. And then so we quickly look over at our knowns and we see, do we have delta t? And we go, we don't have delta t. We got to do a little bit more work. We do know that obviously delta x is plus 3.0 meters, but what is the time? Now we got to look in, I didn't cross my t's there. We got to look and see what we can use to find time. And so looking at these 3 equations in the y direction, how this process goes, as you have found out with your chapter 2 homework, is that, well, you need to look for the equation that has what you need and has what you know and nothing else. And in this case, the first 2 equations, or the first and the last equations, both have v sub 1y, which we don't know, and we technically right now don't need it. One suggestion that people sometimes have is that we could use the third equation to find v final, and then plug in v final to the first equation to find t. but you can show that that's mathematically the same thing as using the second one directly. And the great thing about this second equation for this problem is that that first term on the right-hand side is 0. And so you don't need to use it. So I would write something like to find delta t, right? Use the second equation. Use that one. And so we've got, and fortunately that first term cancels, so we get delta y equals 0, right? So minus 1/2 g delta t squared. Keep that negative sign, and so solve for t. Get delta t equals square root minus 2 delta y over g. Richard, what do you think you're doing? You got a negative sign in that radical. Time isn't imaginary. But the delta y is negative, and so that's going to cancel with the negative sign. And that's always going to work when the launch velocity is horizontal, right? When the launch velocity is horizontal, the particle is always going to move down. It's got nowhere else to go. And so that, the -1 will cancel with the negative sign. You'll be left with, let's see, in this numerical example, we're going to get square root of -2 times -1.0 meters over technically plus, I guess it would just be 9.80 meters per second squared. And so we get an answer of 0.45 seconds. That is our time. But that isn't the thing we were trying to find. Now we just need to plug that in to the very top to show that the velocity in the x direction then is plus 3.0 meters over 0.45 seconds. So you plug that in. This actually isn't that hard to do because when I see a 0.45 here, I automatically think of a 9. And yeah, this is like the same thing as like 30 divided by 0.45 is the same thing like multiply by 2. It's like kind of like 60 over 9. 60, or yeah, it's like 60 over 9. If you multiply both things by 20, always be looking for easy ways to do this stuff in your head. You get plus 6.7 meters per second. So that's the launch velocity. The horizontal launch velocity of the projectile after was dropped at 1 meter for 3.0, and it went 3.0 meters to the right. So now that we have our launch velocity, that's technically the end of that problem. I wanted to also do the next couple parts, which was find the impact speed and the impact angle. And there's a couple remarks I want to make about that after we find that, and then we'll do the graphs. So we're kind of running out of room here, so I will clear the screen and then start over. So what do we do to find V1? That's the easier one of these. Well, because theta 1 depends on V1. Well, V1 is not in those equations, but we have to know that V1 is equal to V1x squared plus V1y squared. It's just the speed, and so we need to know the components. And so we know we just found V1x, right? That is 6.7, 6.7 meters per second. And how do we find V1y? We can use the the third kinematic equation. We could technically use the first of the y equations, but it's generally good practice not to use stuff that you've already found to find other things when you can find them with the problems that are given, because rounding errors can be annoying. So I would do this v1y squared equals v0y squared minus 2g delta y. I would use that. And that is, just plug that in. So that's 0 minus 2 times 9.80. That's technically a 3 sig figs. Displacement in this problem is only known out to 2. Okay, and so when the smoke clears on that calculation, and then we've got all this stuff, 2 times 9.8 is 19.6. I would personally commit that to memory, and as many multiples of 9.8 as you can, and this ends up being 19.6. The units are technically meters squared per second squared, because it's v1y squared, and so I guess it's a little bigger than I planned. And so that is v1y equals 4 square root of 19.6, 4.2 meters per second. Okay. And then so we can plug that in to find the speed. So v1 then equals square root 6.7 squared plus 4.2 squared. You include the units or put them on the outside if you want. I mean, that ends up being 8.0 meters per second. So that's the speed of impact. Notice how the initial speed was 6.7. The initial speed was 6.7, and even though the y component was like 4 meters per second, the speed is only 8. So the speed only increased by 1.3 meters per second. Excuse me, although the y component increased by 4.2 meters per second. Right, that's just the difference between the magnitude of the vector versus the increase in its components. And from a mathematical standpoint, it's just a case of the triangle inequality. But moving on, that isn't as important. The real thing that I wanted to mention was, and I'm going to draw the picture a little bit bigger here, was the impact angle. And so obviously we take a parabolic trajectory as we go from the coordinates maybe 0, 1 to the coordinates 3, 0 on our origin. But the impact speed, if the impact speed is 8.0 meters per second, okay, this angle, and I'm not sure how much to scale this is. Typically, we reserve the Greek letter phi for like impact angle and launch angle as theta. So this is the arctangent of the final component. So it's arctangent 4.2, the y component over 6.7, which equals 32 degrees. Okay, that, sometimes my 7s look like 2s, so I'll just, there we go. That's not, the answer itself isn't as important. What many people like to do, though, is find the launch angle by just connecting the positions, right? So you got a position on the top of vector, 3j, and then a final position vector 4i, or no, not 4, that's another problem. 1j, and then final position of 3i. So what people like to do is connect those dots and then say that this is the impact angle. I tried to draw them a little exaggerated here, but those are completely different angles. Okay, the angle that is part of like the right triangle of the position vectors is not the same as the impact angle of the velocity vector. In fact, if you were to, running out of maybe alpha be an angle, if you were to calculate this angle, it'd be the arctangent of 1/3, right? Because this side is opposite, this side is adjacent. So tangent of alpha equals 1/3, and so invert that, and so we get 1/3. That actually equals about 18 degrees. And for these types of problems, when the particle is moving downward, you can show that this angle. How do I say this? Make this a little bit more formal. The angle, the arctangent of delta y over delta x, when it's moving downward, is always less than the arctangent of Vy over Vx. Makes sense? Right? Because this is the secant line that connects the position vectors. It's always under the trajectory. And so at every stage, that angle is going to be smaller. Because since the trajectory is always above the secant line, I mean, draw a parabola, these secant lines are always under the parabola. Actually makes the parabola in that context what's called convex. But yeah, that's the more general statement. You can even show how Vy and Vx are related to delta y, and you can show that that equals like, what would it equal? Vy would be, let's see. Well, I don't want to get too theoretical, but it probably would be like, if it's this square, it'd be just square root of 2g delta y over the bottom, which would be, let's see, Vx equals delta x over delta t. So yeah, I guess you can show that that is always less. Arctangent has some property that it's always increasing anyway, I'm getting a little more mathematical, but that's just something to keep in mind when you're looking at these parabolic trajectories, is that those two angles are in general going to be different. And when the parabola is concave down, no, not necessarily when it's concave down, when we're on the part of when the parabola is decreasing, then those angles will be different like that. The last thing I want to mention about this example is the graphs. And in these graphs, well, we have now we have graphs for each component of position, velocity, and acceleration. So we'll have our acceleration graph. Don't draw the acceleration graph too big. You'll need the room for the other ones. And then velocity, and then position. Oops. Label this stuff. So accelerate, and all of these horizontal axes are supposed to be time. So I'm not going to write all of them. And this occurs in 0.45 seconds. So what does the acceleration graph look like for x? It's just 0. Well, that means the slope of the velocity graph has to be 0, v sub x. And indeed, it stays the constant 6.7 for those 0.45 seconds. This is a rectangle. If you take 6.7 times 0.45, you get pretty close to 3.0 meters. That area is precisely the change in position from our starting point, which is the origin, to our ending point, which is 3 meters. That's slope. Slope of that line is plus 6.7 meters per second. So as far as the graphs of x, position, velocity, acceleration in the x direction are concerned, this is just an object that's moving to the right with speed 6.7 meters per second. Now, what about the y direction? As far as the y direction is concerned, and they just don't look like they're stacked up very neatly, but ax, that's just going to be a minus 9.8 meters per second. Okay. Again, it's t. What's this area? Well, this is a negative area. If you take 9.8 times 0.45, you're going to get very nearly minus 4.2, which again is exactly the difference in velocities, 0. And then at that time, it's 0 plus the area, which is minus 4.2. Slope of the velocity versus time graph inherits the same relationship that position velocity does. The slope should be minus 9.8 meters per second squared. And then finally the position versus time graph in the y, that is the one that actually looks like the trajectory. You got to be careful though, because it's not a trajectory. It's still just a position versus time graph. And so for those 0.45 seconds, we start at 1 meter, and then it's just a parabola. What would be the equation for this parabola? It would be 1.0, zoom in, it'd be 1.0 meters minus, minus 1/2 gt squared. Half of g is 4.9. I would also commit that to memory. Be minus 4.9 meters per second squared times t squared. So graph that on a calculator. That is the y of t function that you're going to get. Sure enough, you differentiate that, right? d sub y, which is equal to dy dt. You get what? Well, the 1 goes away, and then bring the power rule down. You get 2 times 4.9, so you get minus 9.8 t. With units, correct? And then take the derivative of that again. You get a constant minus 9.8. So we see all sorts of different kinematic relationships on display in these 6 graphs, all related by time. And that's about the last thing I want to say about this example. Actually, one more thing to mention about this graph is that we can find a trajectory, because the trajectory is a function y of x. And so we actually have x as a function of t being 6.7 meters per second times t. Well, obviously the derivative of that, v sub x, which is dx dt, right, is the simple constant or power rule for linear functions. So that's plus 6.7. And then acceleration down here is the derivative of a constant, which, as you would expect, is 0. What's the trajectory? Okay, typically trajectories are given in terms of y as a function of x. I think we mentioned also this a little bit more in a later chapter, but the trajectory would be y as a function of x. And so what you can do to find it is, well, you see y equals, what did I say, 1.0 meters minus 4.9 t squared. Well, what you can do is, x of t is plus 6.7 t. Solve the x of t function for t of x, and then plug it into the y. So t equals x over plus 6.7. And then so if you plug that into the top thing, you get that y of x is 1.0 meters minus, and I'm not going to combine the numbers, minus 4.9 meters per second squared times x over 6.7 meters per second squared. You got to make sure those units look good. Those units look good. Yeah, I mean, we got a meters squared per second squared here. We have a meter per second squared, and so the second squareds will cancel, and we'll have a meter of a meter squared here. Oh yeah, we'll have, yeah, this whole unit analysis of this whole term, it'd be meters cubed on the top and then meters squared at the bottom. Yeah, because you have a meter here, so that's just meters cubed. And then the second squareds cancel, but you have meters squared at the bottom. So that makes sense. And in general, this would be like y naught minus, 1/2 g x over v sub x squared. So you plug that into your calculator, you'll get the actual trajectory that we started off with, 1 and 3. So that's a quick little review about trajectories. In most cases, the trajectories can only really be solved numerically because the equations of motion for x and t, if they're not parabolic, or if there's something else besides quadratic, then in general you won't be able to solve it that way. But in this case you can. Okay. So that officially concludes my discussion on relative motion, or sorry, on projectile motion. I want to move on to relative motion with the last few minutes that we've got. I'm going to unshare real quick and then get on the slides. Again, I'm trying my best to simply review, not lecturing as if you haven't seen any of this before, but just mentioning the high points. Reference frames. What's a reference frame? This is something that physicists really enjoy, especially the higher level you get. So a reference frame is kind of a generalization of the idea of a coordinate system. So in general, you have two coordinate systems, right, with different origins and may even have different orientations. In this case, the coordinate systems are the same side or the same orientation, both x's to the right, both y's up, but there's nothing that requires that. Basically, if you want to know the location of an object, the position of an object will, like I said in the very beginning, vary from coordinate system to coordinate system. And in order for two experimenters to agree, they need to measure the position between their origins, and also perhaps the orientation of the x's and the y's. In this case, it's standard. And so that is the position of an object. So what they do is they say the position of an object, so it's object C. So this is read, this bottom equation here is read, the position of C, object C, relative to experimenter B. And you see here that it's the position, the vector addition is r sub CA plus r sub AB. And that follows r sub CA is the vector on the r sub CA. Oh, it's that's right. The vector on the upper right hand side, and we're adding r sub AB. So we're just like taking this bottom one, moving it to the top, and that sums to the one on the left. Okay, so that's how observers agree on positions. But more importantly, we have to agree on velocities when an object is moving. So just take the derivative of that equation. Easier said than done in principle, because technically, at least in this example, there's only a velocity of one of them. Later on, we'll get to examples where the coordinate systems might be rotating. And when coordinate systems are rotating, that introduces a new feature called the Coriolis effect, and these centripetal effects, which we'll talk about the next lecture. Okay, so let's do a quick example. Actually, before I do that example, let's make sure we understand relative motion. So this equation box down here is that the velocity of an object C, okay, if it's relative to B, is equal to CA plus VAB. And, you know, we got a few minutes before we jump in and do that quick check question. Let me go onto the whiteboard and just do a very, very simple example. And it's an example of you driving on the highway. All right, so your car A. I don't draw cars anymore. Kept being too much of a distraction. So you're driving 60 miles an hour east, for instance, right? And let's say car B, right? This all happened to us. Car B passes you at 70 miles an hour. Right? Where do these velocities come from? These are technically, this is the velocity. These need coordinate systems, and this is all with respect to some coordinate system that is fixed on the Earth. So we'll call it x sub g, wherever the origin is. As we know, velocities don't care about the origins of coordinate systems because they only depend on changes. So this is like velocity of B relative to the ground. And this is the velocity of A relative to the ground. Technically, they need pluses because they're vectors in one dimension. But there's a tree on the side of the road. If it's winter, it's not going to look like that. But the question is, what does everything look like in A's reference frame? So A has its own reference frame. It's got its own meter sticks, and it's got its own stopwatches, and it's got its own coordinate system. Excuse me. You can call it the origin if you like. What does B look like in A reference frame? For that matter, what does the tree look like? Well, your intuition tells you that the tree is kind of moving backwards. And this is your experience, right? Moving backwards at minus 60 miles an hour. And so let's just make sure we can get the notation right for this relative motion equation. So we got V. So what would be the velocity of B relative to A? Oops. Well, it is the velocity of B relative to the ground. See, this inner symbol has to sort of cancel, plus the velocity of the ground relative to A. So what are these? Obviously, BG is plus 70, but what is V sub GA? Well, it's actually the opposite of V sub AG. It's the opposite vector, right? Because you're driving 40 miles an hour east, then the store on the side of the road looks like it's traveling 40 miles an hour west. And that's the idea. So this is actually negative 60. And so we got plus 70 miles an hour plus a minus 60 mph. I'm running out of room. And so we get what you might have expected, which is plus 10 miles an hour. It looks like they're passing us. B looks like they're passing A with a velocity of 10 miles per hour to the right. So that's a very simple one-dimensional example of how to work this notation here. Okay, we got the ground, the two reference frames here are the ground frame and the A frame. So now, with that, the last thing we can do is a quick check question. Double check, yeah. So I'll launch this poll and then we'll discuss the answer. So in looking at this example, it's important, first of all, to establish what these velocities mean, because we have different reference frames. We have a conveyor belt and we have the ground. This 4 meters per second is the velocity of the mouse relative to the belt. Right? Because if you read the problem, mouse sees a blah, blah, piece of cheese and heads straight for the cheese at 4 meters per second, but it's on the belt. What is the 3 meters per second? That is the velocity of the belt relative to the ground. And so the question is asking question is actually asking more than we might expect. We need to use relative motion to do the mouse relative to the ground. And that is equal to the velocity of the mouse relative to the belt, plus the velocity of the belt relative to the ground. You got to keep these inner terms, got to keep these same letters on inside so they cancel. And so that will equal, what's the velocity of the mouse relative to the belt? It's just 4i meters per second. Velocity of the belt relative to the ground may be like 3j, minus 3j meters per second. That's not the answer though. The answer is the actual speed, right? So it's something like this. You got to find the magnitude of that vector. It's a 3, 4, 5 triangle. Those 3, 4, 5 triangles always show up in the most curious places. So certainly the answer to this question is E. So you'll encounter problems like that where you have like a conveyor belt or a canoe crossing a river, or like a, I don't know, like a spider floating on a current or something, those types of examples. So that that concludes this section on relative motion. We'll certainly continue with circular motion next time.